Hello guys, welcome back to my channel. Today I have an interesting integral from Hong Kong, one of the entrance exams of Hong Kong. So let's get to it without further ado. So we have I, which is defined as the integral from negative pi by 4 to pi by 4 of sine of 2x over 2 plus cosine of 2x the whole thing squared times the natural log of 1 plus e to the x power. Yes, it might seem crazy, but don't get intimidated. First off, one great observation is that, well, the derivative of uh, 2 plus cosine 2x with respect to x obviously is negative 2 sine of 2x. So first thing that you can observe is the negative half derivative of the denominator is on the top. So this in the most ideal scenario would call for a substitution. But the only problem is this natural log expression that we have over here. Now, looking at the form of the argument 1 plus some variable, you might think about using Taylor expansions, but in this video I particularly wanted to do this integral the old fashioned way without any infinite series or any weird stuff like that. So noticing that our upper and lower bounds are negative pi by 4 and pi by 4. I mean, you might say that they're symmetric about 0. So we might try to exploit symmetry. So that's going to be my technique. I'm going to exploit symmetry, and the way to do that is you take x and change it to upper limit plus the lower limit. Here is negative pi by 4 minus x. Well, these two just cancel off. So in a sense, x changes to negative x. And when you do that, the rest of the integral remains the same. I mean, you can prove this property by just directly substituting x for like a negative variable, say x equals negative t or something, and then you end up with a similar expression but in t. And then since it's a definite integral, changing the variable doesn't change its meaning, so you can then back substitute into x. Well, but for now, for our convenience, we can directly use this technique. So everything else remains the same. Now sine of negative 2x is negative sine of 2x, because sine is an odd function. But however, cosine is an even function, so cosine of negative 2x is just cosine of 2x, and then this becomes 1 plus e to the negative x power dx. Now one thing you can do here is convert this e to the negative x to an e to the x, by bringing it in the denominator, so and cross multiplying. So we have the integral from negative pi by 4 to pi by 4 of negative sine 2x divided by 2 plus cosine of 2x whole thing squared times the natural log of e raised to x plus 1 over e raised to x dx. And at this point, let me remind you of a very important property of logarithms. Say we have the natural log of b by a. This can be split as the natural log of b minus the natural log of a. So whenever we have a quotient in the argument part, we can write that as a difference of two separate logarithms. So I'm going to use just that. So this is going to be ln of e raised to x plus 1 minus ln of e raised to negative x. My bad, not e to the negative x, just e to the x, because we're not changing the denominator argument in any way. So let's get back. We can totally split this into negative integral from negative pi by 4 to pi by 4 of sine of 2x divided by 2 plus cosine of 2x, the whole thing squared. Then we have ln of e raised to x plus 1 term here dx, and like the second part we have, well, a negative because there was a quotient, and then there was also initially a negative, so in totality it becomes a positive integral from negative pi by 4 to pi by 4 of, well, we're gonna have natural log of e to the x, aren't we, which is nothing but x. So x times the sine of 2x divided by 2 plus cosine of 2x, the whole thing squared dx. Now, fascinating observation here, right now, is this entire thing is our original question I. And let me just scroll up and you can see original question, this thing over here is exactly replicated over here. And that's the best part of using symmetry. You can get your question back in the expansion. So I'm gonna say I is equal to negative I, this was negative I, plus this integral from negative pi by 4 to pi by 4 of x times the sine of 2x divided by 2 plus cosine of 2x, the whole thing squared dx. Now by the linearity of this integral I can add I on both sides, so this I just vanishes and we have 2I equals integral from negative pi by 4 to pi by 4 of x times the sine of 2x divided by 2 plus the cosine of 2x, the whole thing squared dx. So basically what we have to do is we have to basically calculate this integral and then divide the answer by 2 and we obtain our original question I. So I'm gonna do this on a separate page. Now looking at this, we have an x and we have a term we can integrate. You know why we can integrate this? Because as I had said, the negative half of the derivative of the denominator is on the top. Yeah, so in the ideal case, if say there wasn't any x, we could have simply done a substitution of this part. But we have an x, so the only viable candidate here is integration by parts, because say we take x, if we differentiate x and integrate the other bit, differentiating x once will give 1 and basically it'll vanish essentially. So let's do the DI method. Give x that we want to differentiate and we want to integrate this other function, sine of 2x divided by 2 plus sine of 2x, the whole square. So the derivative of x is just 1, and when we integrate this, so before integrating, as I said, the sine of 2x is the negative half derivative of this inside argument of the denominator, so we can totally multiply and divide by a negative 2. So we have negative 2, and then we also multiply by a negative half. So then this part is, the numerator is exactly the derivative of the argument of the denominator. This is exactly the derivative of 2 plus cosine of 2x, as I said, and we have this negative coefficient. So we just going to write the negative coefficient as it is, and then I'm not going to show you all the substitution, but if say we were to substitute this, the top part will become du, the bottom part will become u squared. So now the integral of du over u squared is nothing but 1 negative 1 over u, negative 1 over just the argument of the denominator, and well, basically the negatives become a positive here, 1/2 divided by 2 plus the cosine of 2x. Yeah, that's our antiderivative for this. So we are going to multiply this and this. We'll have a positive sign beside it, and then this and this term, the product of this antiderivative and this one will be in an integral sign, because let me remind you, according to a formula, say we have u dv, that becomes uv minus integral of v du. So if you call this u, you call this dv, then du is 1, and this thing is just v. So basically 2I becomes, x remains unchanged in the first because we have a u into v. So x, I'm writing the half coefficient outside, x by 2 times 1 over 2 plus the cosine of 2x. Well, this is the part that's not in the integral, evaluated from pi by 4 to negative pi by 4, minus a half. Now this part is under the integral sign, minus pi by 4 of dx. We have a 1, I'm just ignoring the 1, dx over 2 plus cosine of 2x. Now we can easily evaluate this this part that is not in the integral sign by substituting the upper limit and the lower limit. So when I substitute the upper limit, I have pi by 4 instead of x, so pi by 4 divided by 2, so essentially pi by 8, and then in this bracket 2 times pi by 4 is pi by 2, so cosine of pi by 2 is 0. This thing will go to 0 in any case, and I'm just left with this 2, so pi by 8 into this 1 by 2, so I have a pi by 16 here, and I'm going to subtract with, when I substitute a negative pi by 4, so negative pi by 4 instead of x, so I have a negative pi by 8 because of this, and then again cosine is an even function, so even for cosine of negative pi by 2, this is again going to go to 0. We have still the 2 left, so in a sense we have a negative pi by 16 minus 1 by 2 times the integral of minus pi by 4 to pi by 4 of dx over, I want to write this 2 as 1 plus 1 plus cosine of 2x, and you will see in a minute why I did this. So basically just calculating this thing, so pi by 16 minus is of minus pi by 16, so basically I have 2 pi by 16, which will make it pi by 8 minus half integral from negative pi by 4 to pi by 4. Well, before going further, I would like to remind you of this trigonometric identity of double angles that we had. So we had 1 plus cosine of say 2 theta is nothing but to cosine squared of theta. So essentially this angle is getting halved, so it's almost like a half angle formula. So I'm going to apply just that over here, because that's exactly why I separated this one from the two. So I have dx over this 1 remains plus 1 plus cosine of 2x is just, according to a formula, 2 cosine squared of x. The angle got half. Well, what can we do now? So we have a pi by 8 which is just lying there, minus half, and then why don't we uh, divide the numerator and denominator by cosine squared. Now this is a standard integration tactic when you have say square trigonometric functions, because if we divide by cosine squared in the numerator, we obtain a secant squared x. And the best thing about a secant squared is it's the derivative of a tangent. So we can essentially write the denominator in terms of a tangent, and we already have the derivative of the tangent on top, and then we can do a grand substitution. So dividing by cosine squared, I obtain 1 over cosine squared is secant squared x plus 2 cosine squared x divided by cosine squared x is just the 2. Now 2i is nothing but pi by 8 minus half times the integral of negative pi by 4 of secant squared x dx as it is. And now I know that secant squared x is nothing but 1 plus tan squared x, and we also have a plus 2 here, so 1 plus 2 is a 3. So essentially have this in the denominator. Now we know that the derivative of tan x is sec squared x, which is in the numerator, so we can do a beautiful substitution. Say w equals tan of x, dw will equal secant squared x dx, and we can change the limits too. Let's do that dynamically. So 2i is equal to pi by 8 minus half secant squared x is nothing but dw divided by, I'm going to write this 3 as root 3 the whole thing squared plus w squared. And now when x is negative pi by 4, tan of negative pi by 4 is a negative 1, and when x equals pi by 4, tan of pi by 4 is 1. So that's how our limits of integration change. So essentially this is just pi by 8 minus half into, this is a standard formula for the inverse tangent type integrand. So 1 over this coefficient that was under this, that was inside this square, times the inverse tangent of the variable divided by the coefficient inside the square. But we still have to evaluate from 1 to negative 1. So let me just do that. So I have pi by 8 minus, I'm going to write the coefficients outside, 1 over 2 root 3, and in the bracket at first time I'll have the inverse tangent of 1 by root 3 minus the inverse tangent of negative 1 by root 3. This is a 3. So let's evaluate this further. We can evaluate it. 1 over 2 root 3. Now the inverse tangent of 1 by root 3 is 30 degrees or pi by 6 radians. And the inverse tangent of negative 1 by root 3 is negative pi by 6, and negative and this negative will make it positive. So I can simplify this to pi by 8 minus 1 by 2 root 3 times 2 pi by 6, and the 2's cancel out. So in the end I have 2i equals pi by 8 minus pi over 6 root 3. Now I can simply divide both sides by 2 to obtain I, which is pi by 16 minus pi by 12 root 3. And let me give you an approximation how much that is. That is about 0.045195938 such a weird answer to a weird integral, if you may. So I guess that's it for this video, guys. If you have any doubts, you can always use the comment section to reach me. And please share this video, please like it, please subscribe. Have a great day. Stay home, stay safe.